Can space-time be non-fundamental? What a silly question could this be for a day like this? Today it's Halloween, obviously. Well, not obviously, but I can say that I do not dress up uh, like hermetic magician like every Tuesday. But it's okay for a day like this because it's Halloween, and it's okay for such an interesting question to talk about. And I just expect not to distract you at all from this amazing topic. Um, well, what a silly question because, well, why not? I th- I'd say Newton. We could say that set up things pretty accurately about space-time because we can say that he was probably the first to set very solid definition and concepts and framework about space and time because we probably had a reasonable understanding about space and time previously, but he was, I'd say, the first one to set very accurate and well specified concepts about space and time, and um, like in order to be able to discuss about concepts and quantities and actually do science and physics on top of these concepts, uh, like for instance calculating velocity and acceleration and force and so on. Um, by the way, this was the kind of science and physics which took us to the conception of space-time being something like a pool, like a pool table for playing on pool, where a pool where um, balls were the particles and the objects, and they were doing the collisions and things like this, and very well determined trajectories. If you know the state of the system at some point, you know, on the laws governing it, you can infer the state of the system at any arbitrary point in the future or in the time. And but this mechanistic overview was reigning for several centuries. At, well, probably until Einstein came and kicked the table and say, okay, space and time, they are not so static and so immutable and so passive. They're not just kind of a scenario for things to happen on top of them, but they play like more dynamic role where we can bend and shrink and elongate and depend, obviously not in our day-to-day life, but yes, close to some extreme conditions like um, uh, close to the speed of light, in places or in points where we have extreme curvature for space time uh, surrounding massive objects where gravitational field is very intense. Uh, Not our daily experience. So Newton's framework and concepts were valid for most of the science that we were needing until then. But definitely, we found that we had not so static scenario. It's more dynamic. It's more actually he placed together as within the same bundle the geometrical dimensions of the space, the geometrical space, uh, together with the time component, which was something new at that time. So they can deformate somehow interchangeable um, time and space in this framework for special and general relativity theory. So that was a breakthrough, but we take space-time as given for any of our concepts and ideations about any kind of problems that we have about the nature of our reality. Mm, but what about not being fundamental? It's a very remarkable question. It's not one that we need to face or experience in our daytime, um, but probably it's a good exercise for trying to comprehend more deeply about the nature of our reality. And I like to think about this. And well, I'm not the one creating these theories or ideas, or I'm just trying to digest them and use them for me to investigate the natural reality from my own eyes. But mm, a proper, a reasonable way of thinking about this is from the point of view of emergence. Emergence in the domain of complexity theory, chaos theory, uh, is the kind of behavior that, or the kind of properties that we get for systems which are not explainable at the level of the individual components made in making these systems. Um, and beyond the twist in the tone about this expression, we can think, for instance, in, for ants, an ants colony. Um, an ants colony, we can find in them air conditioning systems. We can find in them agriculture, um, very complicated structures. Um, if we look it from outside, it looks like a pretty cool design. Um, it's an amazing scale from the point of view of the ants. Um, and how can ants build these kind of systems, these kind of complex structures? It seems difficult to explain at the level of the ant. And that by itself is not pretty much intelligent at all, we'd say, but the next colony seems to manifest um, some traits of intelligent design, if we can use the expression, which is difficult to attribute to individual ants. Mm, for emergence to happen, and it's always surprising. The key idea about emergence is the surprise that how can some so simple components to build up these complex systems. Um, the core to the answer lies in massive repetition, huge, huge tons of huge amounts of iteration, one after the other, and a certain degree of density. Because if we put together many ants, but they interact among them too sparsely, too infrequently, we do not get any interesting behavior or any interesting structure or any interesting top level thing on that. On the other hand, if the interactions are too dense and too frequent, like in a graph, every one connected to every other else, to everyone else, um, it doesn't it, it doesn't work neither, because we got kind of a cacophony of noise. It saturates. So the, the level of density of interactions should be at some cert, at a center at a certain level, in abundant density, where we get the emergence of these top level behaviors. It happens as well many other places, but remarkable places that come to my mind could be um, neural network models for artificial intelligence. if we want to think about that. We want to say that that's intelligent. Um, New models or frontier models today, 2024, they exhibit a reasonable amount of sophistication in the amount of cognition that they can perform. Um, when we think about the components of the model, it's just very simple neurons working and performing code and little computations, but stacked together in many layers, going very deep, and very complex layers with a lot of neurons, each of them. But each of them is, I'd say, simple, especially if we compare with the sophistication of the output. Um, we can think about the level of iteration as well, because the iteration here comes from inconceivable sequences of tokens, which are little pieces of text, so probably less than we can get several tokens out of a simple word. Um, uh, Basically, these models are reading the internet several times, once and again, until their eyes bleed. And by force of repetition, these get to a level of understanding about the text that they're being fed, which force them to um, perform this deep semantic cognition. Um, the key with emergence and complexity is we know that gradually, when we add more iterations, more passes through the data, when we add stack more layers for the neurons, for the model, we know that there is a gradual process of increasing complexity. And we start from having not much to having uh, pretty sophisticated behavior. But it's not clear where to place the frontier between silly and intelligence. And that is one of the uncomfortable things about complexity. You cannot predict the level, you cannot set up clearly a frontier about where do we not we do not have the complex behavior yet, and where we start having them, or when starts to manifest them. That it's, I'd say, for me, the most uncomfortable thing about this, not being able to say, okay, here's where it started. Below this is not intelligence. Um, what has to do all of this with space-time? Well, um, emergence, it's a way of explaining surprising properties about very simple basic components. Maybe space-time can be explained from this mind framework. One of the best, one of the possible gateways to enter this way of thinking is answer the question of what are the components, what are the basic components of space-time. And I think a plausible option will be um, quantum entanglement. Great concept, great thing to talk about as well. Quantum entanglement. Two particles are quantum entangled when they interact one another. Maybe they're created as a pair of particle-antiparticle or something similar. Maybe we can think about two electrons having opposite spins, um, and they are entangled because of that, because the amount of spin any that any system has to be constant and balance itself. Maybe two photons that share some interaction and then polarized in different directions, different planes. And we think those could be entangled because of that as well. And saying that if we look into the polarization plane of one photon or the spin of one electron, and the quantum entangled part, the quantum entangled partner, instantaneously, we know about the state of them. And I'd say instantaneously, and I'd say no matter how long. And if you have not think deeply into that, if you are if this is not uncomfortable to you, maybe you need to think twice about this and get a second thought about it. Try to get deeper, because if we try to assimilate that, again, it's very uncomfortable because it goes beyond time and space. It's instantaneously, it's instantaneous, and it's no matter how far, even if they're at opposite corners of the universe. Um, the one, the second one, the property of the state of the second particle is determined instantaneously. It's uncomfortable for me. I hope for you too. Um, and well, the thing is that when Einstein called this with the alias of the spooky interaction, because it's spooky because it's so unlogical to think that something can go beyond time and space, because we assume that the things that are here, or things remotely far away, opposite corners of the universe, we cannot expect them to affect us. That is that will be a crazy world. If something remotely affects us instantaneously, it's not. It defies the nature of the reality that see around. But it seems to be happening. It is true that it has some um, tricky points, because the quantum entanglement says that it's more about measure and not so much about action. So if I change the spin of one of the electrons, I do not expect the spin of the other one changing instantaneously. Uh, that will be a remote effect, a remote action, to, or a remote reaction to an action. But it's not the case. We only can say that we can measure something and instantaneously know about the outcome of the measure in the case or whenever we go and measure the other one. So somehow it preserves locality, but not fully, because the certainty is there and it's instantaneous. So it's a good building block for something that could be the source of space-time, because it goes beyond time and space. So it has to transcend it, to be the layer, the latent component producing the space time. So how could we think about this generating space and time? Well, we think firstly about space. Space is only measured by a quantity, is characterized by only a quantity and its distance. We can think about ways to encode distance uh, in terms of intensity of quantum entanglement between particles in those 2 points. So if we got 2 points, the more particles, the more pairs that are quantum entangled uh, between those 2 points, the stronger the connection is. And in terms of space, we can say that they're closer. The distance is lower, and we can think about more distant points in the space by being by sharing less quantum particles, or less quantum pairs, quantum entangled pairs. So we can think about this as well in this way. Mm, if we have that, then we can think about trajectories of movement, like traversing this kind of network and going from, if we were thinking about railroad, we can think about going through stations, through train stations, and there are some certain links, and we can go from one point to another the same way that we go from one station to another train station by using the links in between them. Here, the links are the quantum entanglement of pairs of particles in between. So it's a way to encode it. I couldn't say I have a demonstration for that, but it's something to start to work with. Um, what else to say about this as well? Another strange thing is that who is first, the chicken or the egg, the chicken or the egg? Here we get the same for which is first, in space or the matter, the space or the particle, because we usually think that particles move around space. So we take space as given, and the particle are something happening on top, or moving on top of that. But here is not exactly, because particles are creating the network that defines the fabric of the space-time. So it's, once more, it's strange and it's uncomfortable. Um, but it connects and it makes sense from the point of view that, for instance, it always felt strange to me that Big Bang created space-time. So the same way, we expect space-time be given, and the Big Bang happens on top of that and creates matter and energy and so on. But it's well established that the space-time has been created in the Big Bang. So um, the particles and the matter and the energy uh, getting out of this primordial explosion could be creating, um, are within their expansion, with, as they expanded, they were creating the space-time just simultaneously. Uh, we can take this word for this, and it could explain that, and it's coherent in this way, thinking that uh, space-time was created out of Big Bang and not before. Uh, some other interesting things about this, um, having this network or this non-fundamental nature of space-time um, implies a discreteness in the nature. I mean, uh, in between 2 points of this quantum entangled space-time, in between there is nothing. Let's call it void or something like that. I don't like to call it void, but there's nothing. No, we say. So it's a discreteness. So, but it's very good. It's very good for some reasons. For instance, across many theories, across many equations in these theories and mathematical models, we encounter very big problems, infinite problems, which are related with distances being placed by the equations in the denominators, effectively yielding infinite amounts. It happens for for several quantities. For instance, we got infinite curvature or infinite density and singularities in relativity theory, because sometimes things could be infinitely closed. And that is a problem, and it causes a lot of inconvenience, and seems not to be happening at all in our reality. A more obvious or more tangible way to think about this is electrical attraction. We got infinite forces for electrical attractions, as long as particles are as closely as we want to place them. Um, as well, the same is not this 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 does not seem to be happening at all in our world, like having infinite forces, and probably there is no infinitely close distances. And this resolution limit that we can think of, like the TV, when looking to that closely, and we say and we found that there are pixels instead of a continuous picture. Um, it could happen the same with the space time. And what other things? Well, this limiting resolution, I'd say that it could be somehow, but not fully sure, not fully convinced, with uncertainty principle in quantum mechanics as well, and saying that maybe this uncertainty and this limiting the precision of our measurements of our certainty is connected somehow with a manifestation of the resolution of the system, resolution of the space-time being manifested out, and say, okay, this is the deeper that you can go. This is, you cannot beyond this limit of precision, and it manifests as as, an, as the uncertainty principle, and when it's lying behind and when it's lying below is the limit in resolution for the space-time itself. I'd say, and I feel more comfortable attributing this uncertainty to the inability to separate the observer from the observed. So, in order to measure something, you need to be a part of the system where it relies, where it lives. Um, that inability to fully separate observer and the observed thing, it goes to the very same limits of our experience of reality. And okay, it's just the uncertainty principle is just uh, shouting out to you that okay, you cannot measure something externally because you are part of it. I think it could be more explain. We could provide a more solid explanation for that, and for the uncertainty principle in this approach, than about the resolution of the space-time. Mm, what things to say as well? Maybe there are people um, and theories out there with non-conformal theories and holographic universe, anti-de Sitter theories, which I'd like to have them a try, but well, it's just an open topic, um, and it's like vanguard in physics, I'd say. And well, I have not entered that. I have not entered there fully yet. So, but I invite you, if you to look into that, to research. And I mean myself, maybe someday I give it a try and see what is inside, and if it is too scary when you look it from outside, um, that will be nice. There are some more digestible things that I've been able to research more carefully. For instance, um, Stephen Wolfram with the hypergraphs, which somehow is stating something very similar to that, but it's trying to place his own thing about the cellular automata and this mind framework, and complexity and emergence and iteration and computationally and computation, and it does very interesting things. He thinks about reality, space-time, and all the particles around as emergent properties of an hypergraph or hypergraph, which is stupidly simple connections that happens between points that were not actually points, but they're just network of causality. It creates and deletes edges in this graph with a very simple rule, which is applied iteratively for I don't know, unconceivable frequencies because it's so tiny and so numerous and should be really fast. I have no idea about specific numbers, and probably it's not at that level of definition the theory. Um, but it's basically doing that, adding and removing links in this graph. Somehow he's trying to find the rule in the system that generates properties which seem to be uh, similar to what we observe in the real world. And, I read that briefly and about a couple of years ago, probably, or 3 years ago. And I found very interesting ways of uh, deriving relativity theory out of this, connecting computational irreducibility with the uncertainty principle from quantum mechanics, um, deriving speeds, the limits in the speed of light. It was very unorthodox, because of that, very appealing. It's interesting. I don't know the amount of progress that could have been there during the last few years, but definitely it's something to look into it if you are in the mood for that and you are not scared of strange things because it's strange. Um, yeah, um, it's even weirder because we've only talked here about the discreteness of space, and implicitly we were referring to the geometrical dimensions of space. But think about time. Time being discrete. And so between an instant and the next one, there's nothing in between. Think about this again. Between an instant and the next instant, there is nothing in between. You want to fight and struggle with that? Go ahead. But it feels bad. But it feels bad. Um, Following the analogy of the TV, the here the resolution is a picture and nothing in between, and only because the inability of our eye to see the gaps in between, we've got this illusion of continuity, of fluidity that looks to be a movement there, but there's no movement. There are a succession of individual frames. I'm thinking right now about show Truman Show, the movie, and touching the what looked like the like the night sky or like the the heaven, and touching that feels it's strange. It's probably the same sensation that you've been living an illusion for all of your life, and thinking that the most fundamental things that you took for given are not that way actually from the very beginning. It's it's such a strange feeling. Yeah, but I'd say why not? I cannot say that it's proven. I cannot say that it's demonstrated. These are not the theories of me. Obviously, I'm just a guy looking out there and see what's happening and try to make sense and exercise my mind against these uncomfortable ways of thinking, and, and trying to challenge my assumptions and have less assumptions and go deeper there. Uh, it happened in the past. Uh, the movement from a continuous conception to a discrete conception, it happened several times across the history of our the knowledge of the human species. And um, well, not far away, not long ago, we used to think that matter was continuous instead of made of single atoms. More recently, we realized that even the atoms were mostly made out of void. Uh, Void, strange, but uh, nothing in between. So nucleus and the electrons around so sparse. It's difficult to think of, and it's not so continuous as it looks from outside. Maybe just because we've got not the resolution in our measurement systems, in our way of interacting with reality, or in the amount of the depth of the ideas that we can convey about the nature of reality. Um, yeah, from that point of view, even if it's surprising and very strange things here could happen, and very far away from what we see and experience daily, I wouldn't be surprised that um, it happens again. That we can say that space-time is not fundamental, but made of something else, more fundamental, or building blocks, and all the consequences that it would have for our idea of the world and for the things that we can do with the things around. So yeah, that was all for today, and I just wanted to wish you a happy Halloween, and keep enjoying all these good ideas that they're out there, and they're, I'd say, unlimited. So see you next time.